I can't use my desktop computer at the moment because it's broken at the moment. So I'm instead using my tablet. I'm using just OBS Studio to record my voice, unlike using a microphone, which I did earlier. So hopefully it'll be clear as possible. And today I want to be talking about passive and active sensors. And let's just start with passive sensors to begin with. I had a whole lecture on this, but it's all pretty much just, it's not that useful content, so I'm just going to shoot through it in like a second.
So what you have in active and passive remote sensing is that in passive, all that you have is you have a sensor, so this can be a satellite or a plane, or it could also be a balloon or something else, and it uses the sun's light, which is bouncing off the Earth, to get an image of what's on the ground. Whereas in active remote sensing, you have a satellite, plane, whatever it is, to project its own light onto the Earth, and then that rebounds up to the platform again, and then you get an image of what's on the ground. And quickly, I also want to talk about the types of the levels of like spectrality. Based on like how advanced the satellite or platform is, most platforms tend to have multi-spectral light. And if you go to satellites, if you Google up the name of the satellite, it might be like Landsat or something, then you can see which type it has. It might only have like a few bands, and that'll probably be multispectral, or it may have hundreds of bands, and that's usually hyperspectral.
So radar solely uses microwave wavelengths, which are very long waves. And within this segment of the chain of EMR, there is a rather large amount of wavelength variation. Within the microwave wavelengths, which is 1 millimeter to 1 meter about, when we are transmitting it down, it's important to remember that most of the time the image will be side-looking. So why is this, you're asking? Because imagine you're flying a plane directly over a single object. You can do this, but good luck doing it on every single object. It's going to cost way too much. You can't fly a plane over every single building, which is why light being emitted from that plane will always be from the side view at an angle. Any angle depending on how far away it is from the plane. So with this information, we can determine the distance from our sensor to the airplane or whatever we are using, but chances are it's an airplane. The reflectance properties, as we already know, constitutes the object. Now we'll be talking about synthetic aperture radar systems, or SAR. Shown on a reflectance time graph, we know the pulse's strength from a SAR after it's done hitting everything. So first we record the initial pulse that we made. This should be 100% strength. And then we have multiple returning pulses. The microwave antenna should be using the full region it governs, as if we are using, say, blue, green, and red. This antenna is both the transmitter and the receiver, typically, but most of the time it is. And the size of the antenna determines the spatial resolution. SAR image resolution comes in 2 dimensions. These are the range and azimuth dimensions. So the range is the across track, and the azimuth is along this track. And you can see that in that image right there. So the beam or pulse coming from SAR can be polarized using a filter. What's this mean? Well, polarization means to send out or receive a single wave or multiple waves of either of the two I'm showing you here. So this means, from an earlier slide of another video, that we can shoot entirely by electric field and distance, or magnetic field and distance. And you can see that in these slides right here. So the transmitted radar signals can be generated so that the electrical wave vibrations are restricted to a single plane, that is, perpendicular to the direction of wave propagation. So if we shoot out in a horizontal plane, we can receive in a horizontal plane, or we can shoot out in both planes and receive only one. So horizontal H and vertical V are typically transmitted separately. Interaction with features on the Earth's surface can change the polarization of the scattered signal. So if we shoot a horizontal beam, we can receive a vertical back. So HH or VV images are referred to as co-polarized, meaning that we're shooting, that should be both beams, I would think. HV or VH are cross-polarized. Oh, sorry. So HH and VV means we're either shooting in horizontal or vertical entirely, And HV or VH means that we are shooting both and receiving both. Or we can use a filter to stop that. So the polarization mode affecting the scattering intensity echo, and thus how the objects appear in the resulting imagery. So depending on which we shoot, we will get a different image. And you can, if you go back to my very first video in this course, I had the link to this document, which is I'm getting notes from for these videos. So cross-polarization can show different terrain and vegetation effects. I hope you guys can understand that, because going through my notes, it took me a little while to fathom exactly what that was talking about. Anyway, moving on. We have ranging and imaging sequence. Ranging is the process of measuring return time of signals and the time to return, or echo. So this can then be used to develop an image using distance. It's important to note here that distance can be skewed, but I'll explain that later. Also, microwave EMR reflectivity can affect signal strength, called the amplitude. Finally, regarding sequence, note that the shape of the target reflects echoed the signal shape, called ellipticity. So the target reflects the reflected signal shape, the echoed signal shape. This is called ellipticity. Well, so it's a word derived from ellipsis. And the orientation, horizontal or vertical. Spatial resolution, some notes. So spatial resolution is determined by the length of the synthesized antenna and not the actual size of the antenna. The length of the synthesized antenna is determined by the distance traveled by the sensor while receiving signals for a given ground element. So the distance that the sensor covers, the land that the sensor covers. Radar pulses are emitted over very short periods. Pixels that come back as brighter have higher scattering intensities. So, terrain surface influences on radar return. A feature with a slope, like a mountain, will result differently depending on the steepness of the slope. This can create layover, foreshortening, and shadowing effects. And you can see that from these 3 or so images I should have up right now. The further the mountain is away, the less layover, and the more shadowing. If you look at a rock, and if you're not standing directly over it, where you can see the entire rock and you can see everything around it, if you're staying really far away from it, everything behind that rock should be in shadow, which will affect your reflectivity of the EMR that you shoot out to it. With foreshortening, the top of a mountain range can move or disappear. And a digital elevation model can correct these effects. So from these images I'm showing you, just know that these are all essentially angle effects, depending on where the plane is in relation to the feature, or where the camera is in relation to the feature. The feature is the object in question that you're shooting light at. There are also other dependent factors, such as surface roughness, which we would use the root mean square error to measure. So there are a few scattering types. These include the roughness, which is diffuse scattering at all angles, the smoothness, which reflects all incident EMR, and the intermed, which is reflected and scattered. I should also tell you that the more jumps or bounces a piece of reflected light does, the less strength it will have when it returns to the sensor. And since we judge height, or distance, by time, the time it takes for light to get back to us will change. So these features, distance and height, are changeable. So imagine that we shoot light bouncing thousands of times inside a chamber after we projected it, and finally some light managed to get back to us. It would seem as though the chamber is incredibly altered from its real dimensions. So this would be like if we shot light at a box, and then all of a sudden, before the light managed to come out of the box back to us, we shut the door, and so the light is jumping around inside the box a million times. And then we opened the door, and the light suddenly came back to us. It would appear as though the box is really, really far away, when it's not, because we judge distance based on time. The amount of time it takes for the light to get to an object and get back to us is how far away it is. That's how they determine where planets, how far planets are away, or something. So we shoot lights, say at Jupiter, and it takes forever for it to get back to us, we know how far away it is. But if it got back to us in like a second, we could say, oh, it's like a few meters away from us. It's really, really, really close. But, light moves really, really quickly, so take that into account about how far away it is. So, just like one or two more things, I think we're done with this. So, electrical characteristics. We have the dielectric constant, which is a measure of quantity of electrical energy which is stored, absorbed, and conducted through a material. So is energy absorbed by the tree itself, by a tree itself, an object that we're talking about? It's dependent on how much water is in it. Is it got a dry surface or has it got a wet surface? And the changes in the dielectric constant. And then we also have the backscatter coefficient, which is the amount of signal coming back from the feature. This isn't the same as the dielectric constant, which is the measure of quantity of electrical energy stored, absorbed, conducted. But back to backscatter. My final point in this is the strength of radar return in decibels measured in area. So as my pretty much final point, we have interpreting SAR images. Elements of a radar include the sensor type, the radar wavelength, the radar polarizations, the flight direction in azimuth direction, the ranging direction, the azimuth resolution, the range resolution, and atmospheric and ground conditions. So, SAR applications include ecology, hydrology, geology, and oceanography. If that's a field you want to go into, that's what you can go into with SAR. And finally, LiDAR. LiDAR is either pulsed or a continuous laser sent down from a platform with the aircraft positioning, recorded using an onboard GPS, connected to an above GPS satellite. So LiDAR is recording its own position as well as the lights coming back to it. In the receiver for LiDAR, we get multiple returns, with the first being, for example, vegetation, and the final being the ground beneath. So it has relative strength at its final point in the light returning, but it has no height, pretty much. And the height of the ground along the y-axis may change slightly if there is a hill or ridge. And you can see that from this image here. With LiDAR, we can measure canopy to ground height. So that means that with our lights, we're shooting it at a tree. The first light to rebound off that tree and come back to us is the tree's maximum height. And then we have a bunch of intermittent light, which is the light going through the branches, and it gets reflected back, which takes a little bit longer, which means that the height is lower. You can see on the y-axis there. And then finally, the last bit of light will just hit the ground, and then it'll come back to us, and that should be, hopefully, unless physics has changed, that will be the lowest point in height. And its energy will depend on if it was absorbed by the tree above it, or if it was reflected by the tree and it went away. So if the tree was like super reflective and light's going through it that we're shooting at it, and it all gets reflected away, then there should be practically no strength that comes back after first hitting the ground. But anyway, that's the way light works. It hits the tallest object, it comes back. It hits the medium highest object, it comes back, and then it hits the ground terrain, and then it comes back. And so, that is it, guys. I hope you learned something today. I'll be doing my next video really, really soon. We'll be using Envy again, and we should be able to put some of this kind of stuff into practice. So, good luck, guys, and I hope this is clear enough. Really, really soon I'll be getting my desktop back, and I won't have to use this tablet's microphone. But anyway, good luck.